in the intertidal zone must be adapted to a very wide range of temperatures. And I'm sure you've all heard the word thermal, right?
No.
We definitely talked about that.
Yeah, I don't want to be redundant. I know that Tony,
no, don't worry about
Tony and Kristen have educated you all to the nth degree, and so I'm sorry about that. I do get redundant. Eurythermal is a term that applies to species that have this broad tolerance of temperatures. Also, we can have great extremes in salinity within the intertidal zone. If you have it raining during low tide, of course, you have a great dilution of the tide pools and the poor water. But on a bright sunny day, you can have high rates of evaporation and very high salinity. So animals have to be euryhaline, that is, be able to withstand a wide range of salinities. Unlike in the open ocean, which is pretty much constant at about 34, 35 parts per thousand. And then there's the problem of breathing, gas exchange. These animals are all derived from ancestors that have gills. Okay? Gills work fine in water. Gills work fine in water. They don't work very well in the air. So consequently, you'll find that many of the organisms that we collect out here, many of the little snails and other creatures, the crustaceans, have very much reduced gill volume. And on the other hand, the gill chamber has become highly vascularized and modified as a functional lung. So gas exchange takes place between the air within the gill chamber and the vascularized lining of the chamber. So reduction in the gill volume is an adaptation that also prevents evaporative water loss, because the gills have to necessarily be very thin-walled structures, and that becomes the primary site of evaporative water loss. So the threat of desiccation is something else that these organisms have to be able to tolerate or to withstand. So I don't want to belabor this, but what I'm saying is that...
See if anybody knows what animal that is.
Lunch.
Okay. You know what this is. Everybody knows what this is, right?
Ribbed mussel.
Ribbed mussel.
In case they don't know. Ribbed mussel.
And I usually carry one of these around with me. But ribbed mussel exemplifies many of the traits that I've just talked about that characterize intertidal animals. Because ribbed mussels live very high up in the intertidal zone. They live in the salt marsh, and they live attached to the below ground parts of the Spartina. Spartina has these underground rhizome systems. These
you guys switch over to the side a little bit. We gotta leave the beach here. Just some people need to get by.
But you'll find these mussels buried in the substrate with maybe just about that much of the shell exposed. So these animals spend most of their life out of water. So these animals must be able to tolerate this extreme range of conditions. The animal produces these so-called byssal threads. These very tough fibers are produced by a gland in the foot, and this is what attaches these animals to the rhizome systems of the Spartina. But this is a tough animal. This is my personal hero among the invertebrates. This animal can tolerate having 70% of its body fluids frozen, and then it can recover. This animal can tolerate a salinity range of about 3 parts per thousand, which is almost fresh water, up to about 43, 45 parts per thousand.
35 is seawater.
And 35 is seawater. So now, not many animals can do that, can tolerate that range of salinity. And this animal can tolerate the complete absence of oxygen for up to 5 days. So it's a tough animal. You'll notice that there's a tough outer covering, this brownish material. This is the periostracum. It's actually the outer layer of the shell, and that prevents the shell from erosion by the acids. These animals live in anaerobic muds. No oxygen in these muds, so there's a lot of anaerobic bacteria that produce hydrogen sulfide, which would tend to erode away the calcium substrate of the shell.
That's what makes the marshy smell.
Right, right. And so anyway, the shell is very thin, partly protected by this well-developed periostracum. But let me show you some other characteristics of this animal.
They're tough, but not that tough.
Yeah.
Not as tough as he is.
I want to show you what the inside of the animal looks like. Okay.
Hungry again.
Yes.
Okay. Now, these are the byssal threads. These are the gills. And this, you see that little thing there?
Yeah.
That's the foot. That's all that's left of the foot.
Wow.
Right.
And the only purpose of that foot is to secrete these byssal threads.
Huh.
Now, this is in great contrast to most bivalves. You know, most bivalves, like little neck clams or cherry stones, whatever you want to call them, have a well-developed muscular foot. That's mostly what you eat when you eat one of these bivalves. But
Is the foot?
yeah, the foot.
Yeah.
Now, the bivalves are adapted for burrowing in soft substrates as a group. That's how they evolved. And so most bivalves have a very muscular, extensible foot by which they insert into the sand or mud, and then they literally pull themselves down below the surface. But this animal doesn't burrow. It's given up that lifestyle, just like oysters. Oysters don't burrow. Oysters don't have a foot to speak of. It's very vestigial. These animals don't burrow. They just remain attached in one spot, attached by these byssal threads. And so the foot has become very much reduced, and that's all you have. That little finger-like structure there, and its only purpose is to secrete these byssal threads.
And do they renew these byssal threads?
Yes,
continually?
they will, and this is a characteristic of all kinds of mussels. Blue mussels, which are the edible mussels, you find attached to seawalls, intertidal rocks and wharfs and substrates and like that. They have these byssal threads. In this case, they're attached to the underground parts of the plant.
So they need to cluster together like oysters in order to be successful?
You do find them typically in clusters, partly because the shell serves as an attractive settling substrate for the planktonic larvae, you know, and then they will attach themselves to the underground parts of the plant.
And that's a good point to remember, guys. These larvae are floating around in the water. So when you think about how does the mussel get there if it's stuck in position? It's because as larvae, they're floating around and they find the right place and they settle out and they turn into adults.
And many of these larvae, and most marine invertebrates do produce planktonic larvae. And most of these larvae are very substrate specific. They'll attach only to a certain kind of substrate. And I think we'll see some examples of that in the animals that we collect out here today. But it's amazing the degree of specificity that these little larvae can respond to. Some of these barnacle larvae, for example, will attach only to the back of a crab or a horseshoe crab. The gooseneck barnacles, the larvae attach only to floating objects. But we'll see some examples. Anybody ever eat one of these?
Yes.
Yeah, we
Have you?
Oh yeah, I've harvested them off of a marsh where I live.
Do you really?
And eat them.
Uh-huh.
we had them for a bivalve supper.